Okay, welcome back, everybody. We've almost made it through our first week of classes. Woohoo! We're going to keep going in here, thinking about our first specific types of blood vessels that we're going to link up to our new understanding of flow and pressure gradients and this concept called resistance. So I want you to take a look at this problem up here real quick to start us off, a little review of what we did last time. So we've got two imaginary arterioles here, A and B, each of which have a pressure at one end of 90, pressure at the other end of 40, and we've got some radii here. First one, A, has an internal radius of 0.025. Second has a radius of 0.005. So what we're doing here is we're thinking about pressures, resistance, radii, and flow. And on the next screen, I'm going to ask you which of these has greater flow. Okay. So let me know. What do we think? A or B? All right, keep rolling. So take a look. Okay, great. So the answer is A. So what we're looking for up there is those size of the radii are the difference, right? And what we might kind of put things together and remember, right? So we know that flow is dependent on pressure difference and radius, or sorry, and resistance. And we know that our resistance is inversely proportional to our radius. Okay. So when we see a radius go up, that means the resistance goes down, right? So if our resistance is down, that means our flow goes up. So you can also notice here, right, that if you want to skip this resistance part in the middle, you kind of can, right? So for flow to go up, this means a radius went up. And it's that resistance in the middle that's going the opposite direction. Important for understanding like why the flow goes up. But if you're just trying to pair stuff together, you can do it this way too. Okay, great. So now we're going to be thinking about our different types of blood vessels, and we're going to be thinking about some of the structural differences that relate these physical concepts to what we actually see in vasculature. Okay, so for our blood flow, we reviewed briefly, starting from the heart, we have arteries going away, right? A for away, arteries go away. And then we have a series of splits. So our large arteries split, give us some smaller arteries, continue splitting again and again. We get to our microcirculation. So that's the part that's not visible to the naked eye. So now we have a new word for our type of blood vessel at this point. We're still going away from the heart in general. We've got our arterioles. They're going to take us to capillaries, which is where we have stuff actually crossing blood vessel walls in and out. And then we start our return to the heart. Venules are little and tiny, but they're starting that return, and then they move into the veins that are going to be visible in the bodies, return the blood all the way to the heart. And we can see that there are going to be some things that vary in terms of the properties of these different types of blood vessels, right? So what we see in this chart that we might notice is that we're going to have differences in the average internal diameter, right? So we might pay attention to this because diameter is just twice the radius, right? And we now know that radius tells us things about flow, right? So we can see that our arteries have a really wide diameter, right? It's a really big internal diameter, so big radius. So stuff is going to flow fast through an artery, right? Versus by the time we get down to capillaries with this teeny tiny radius, sorry, teeny tiny diameter, which means that the radius is going to be half this, right? We're at any individual capillary going to have slower flow through that capillary so that we have time to exchange materials back and forth. Now, we'll get to what that looks like on bulk for the whole body, but in any individual capillary, this would be true. We can also see that there's going to be some differences between the thickness of the walls in these blood vessels. So we can see that our arteries have big meaty walls. Our veins, I'll skip to the bottom, have thinner walls. So this is going to link up in a little bit with a concept called compliance. We mentioned it with the heart. We're going to think about it more as we think about blood vessels. But you can also already link this up to what you've seen in lab, right? The arteries generally look kind of like white in color. They bounce back if you poke them in the lab. This is because we have these highly elastic, thick walls, right? So they're opaque, so you can't see blood inside. Those thinner walls on the veins make them floppier and also mean that you can see the blood through them a little more in the bodies, which is part of why they have that darker color to them. Now, we can also see that there are some special features to our different types of blood vessels. Right? So we're going to be starting with the arteries today. So we want to know about our arteries. They are going to have muscle tissue in them. Right? So they're muscular and they're going to be highly elastic. So this really means when we talk about elasticity that they like bounce back. Right? We've talked about the aorta bouncing back, maintaining pressure through your systemic circuit in A&P1, and we're going to be thinking more about that today. Our arterioles also have muscles, which is going to be really important for us in the future when we start to think about changing resistance throughout our systemic circuit. Capillaries are super thin-walled, highly permeable. You see there's not this thick outer layer of connective tissue. There's no layer of muscle here, right? This is specialized for what they do, which is that exchange. And then we build back up in our venules and veins. We'll get there in a little while. It's not going to be this week for sure. Okay. We can name those different layers in general of a blood vessel. Okay. So any given blood vessel, we're going to want to pay attention to like what exactly it is, right? We just saw in that previous chart that there's some variation from blood vessel to blood vessel, exactly what components you'd have. But in general, if we're looking at that wall, we're going to refer to that innermost layer of our blood vessel. So this yellow part inside, that's our endothelium, our endothelial layer. So endo, think inside, right? So this is the inner layer. This one is going to be present in all your blood vessels. This is making sure that, the blood doesn't actually spill out of the blood vessel. The other components are the part that varies a bit. So we have that layer of muscle here, right, which we're going to see definitely in an artery, definitely in an arterial, not in a capillary, some in veins coming back sometimes, but going to be important for our arteries and our arterioles. Okay. This layer is specifically made of smooth muscle. So this is not like skeletal muscle, not under your conscious control, but will be important when we link it up to how the autonomic nervous system acts on the vasculature. And we've got our connective tissue out here in kind of beige. So this includes two different components. So we have a fibrous part that's made of collagen, and then we have an elastic part, and that's made of elastin. Both of those are important for giving the connective tissue both like kind of solid structure and also some elasticity to it. Okay. So beginning with our arteries, being blocked, back to the other side. Okay, so our arteries are for rapid transport away from the heart, and their physical properties match that function. So they're big and wide. They have that wide radius, which means we've got a wide diameter, right? And because we have that big radius, that means we don't have very much resistance, low resistance, but we have the ability to put a lot of blood through that quickly because we got a lot of flow through this artery. Now, because we have all this blood flowing through these arteries quickly, we also want to think about how they interact with the pressure of that blood. So the walls of an artery have both elastic tissue made of that elastin and fibrous tissue made of collagen. And these walls are under high pressure from all that blood coming right out of the heart, right? The arteries are the closest to the heart. Our big artery, the aorta, is the first thing that blood hits as we leave the heart. Okay? And we're going to think about that again in a second. We're going to have a picture of the aorta again. You should know that there are smaller arteries, right? We do keep splitting down. Eventually, we get to some small arteries called muscular arteries. These are going to be much smaller than some of the others. So we have less than 0.1 millimeter in diameter. As they're getting smaller, once they get down to this level, they're not going to have much of the elastin left, but they will start to have smooth muscle regulating the radius, which is what we're really going to emphasize when we get to the next level down, the arterioles. So here we have this picture of what's happening in the aorta. We've seen it before when we were talking about the relationship between the aorta and the heart in A&P 1. Now we're coming back to it here. Okay. So what we're looking at, right, this is what our blood sees as it comes out of the left ventricle, right? We have to go through that aortic valve. Right, so that's one of our two types of semilunar valves, right, to leave the heart. So to get here, we had to have a high to low pressure gradient, right? That's how we see that direction of flow. Okay. So once we're in there, as we're ejecting blood into the aorta, right, that blast of blood coming through pushes on the walls, right? So now we know that these walls are thick. This is an artery. They've got elastin, they've got collagen, and they have this elastic property to them. So they're expanding in response to this increase in volume as the heart is pumping out blood. They're going to essentially be kind of like holding and storing pressure in that wall. So they've expanded, but they're ready to bounce back. They're ready to snap back down once that inflow of blood is gone. We think of arteries as having low compliance, and that's about a relationship between pressure and volume. We'll draw a graph on one of the next slides to think about that compliance. Okay, but right now we're just focusing on that artery expanding as the blood goes into the arteries during systole. And then when blood flow stops, right, when this aortic valve closes, right, and it would close because now we have a lower pressure in the heart and we have all this high pressure from the blood that's been shoved into the aorta. We don't want blood to move backwards into the heart, so that valve has to be closing. Okay, so at this point, we have those valves closed, stop the flow, and that pressure that we stored in the wall of the aorta, we have those walls bouncing back, so this elastic recoil back in, keeping that blood flowing now through the systemic circuit. Even though the heart is going into diastole, into relaxation, it's in low pressure, we still have blood flow out to our organs because we're using this stored pressure. Okay, cool. Yeah, so compliance. All right, so compliance is a relationship between pressure and volume, okay? So when we see graphs of this, it's gonna look like this. So we're gonna have pressure on the bottom, so on that x-axis, and then on our y-axis, we have volume, okay? And I'm drawing this for you because I draw this in my mind every single time I think about what does low compliance and what does high compliance mean, because I don't know about you. When I think about it in words, it's more confusing than when I just see it and can read it off a graph. So hopefully this will help you, but if this confuses you, you can ignore what I'm saying. Okay, so volume and pressure. Okay, so we're going to talk about arteries as having low compliance. I'm drawing this line here, low compliance. And later on, when we get to the veins, I think it's helpful to put them on right now. Our veins, we're going to think of as having high compliance. So they're going to have a higher line on this compliance graph. Okay. So what this means for us, we can read it in kind of either direction. Okay. So for now, because we're talking about the artery, we're thinking about this property of having low compliance as turning our arteries into a pressure reservoir so we can keep pressure pumping blood through our systemic circuit even when the heart is resting. Okay, so the reason they can work like this, right, is that you only need a little bit of volume, a little bit of extra volume, right, in order to take an artery to like a really high pressure. Maybe I should curve this up a little more, right? But if our pressure is going up 0, 10, whatever, right? This is the up direction, right? You only had to put in a little extra blood to jack that artery up to high pressure, right? To get the vein to that same high pressure, you'd have to put in a lot more volume. And so later on, we're going to think about veins as being a volume reservoir. Okay, but right now we're thinking about our arteries being a pressure reservoir because they have low compliance. Okay. So I think you have some version of this graph in your book as well. I recommend spending some time looking at it and trying reading it from both the pressure side and the volume side to kind of get this idea of compliance into your mind. All right. So arteries, always low compliance. Veins are going to be our vessel with high compliance, meaning that they're going to have pretty low pressure in them kind of all the time, which is great because we want a pressure gradient, right? We want our arteries to be high pressure. We want our veins to be low pressure because we need that high-low gradient for blood to return to the veins and come back to the heart, right? And we're going to be able to put in kind of as much blood as we want into the veins without significantly changing that low pressure environment for them. They're going to be kind of like our veins will be more like a kind of floppy foil birthday balloon, and our arteries are more like a water balloon that's really hard to get a lot of water into, and if you squeeze it, they pop easily. Okay, that's our compliance. So we're thinking about the aorta specifically now. Okay. So our aorta is our largest artery coming right out of the heart. We know that the pressure in the aorta is going to, by necessity, vary a bit because that aorta receives blood from the heart. Sometimes the heart is pumping out blood, right? And sometimes it's at rest, right? So the heart is going through its phases. It's going through systole and diastole. So we've got a kind of variable environment in the aorta, right? So the highest pressure we see in the aorta, the pressure that we're like storing in those walls, is that maximum pressure that we have during systole, right? So when the heart squeezes, right? So we have that ejection of blood into the aorta. We hit our systolic blood pressure at that maximum pressure. Now, then our heart relaxes, right? We cycle back to the beginning of our cardiac cycle. We're going back to our ventricular filling, right? Heart's at rest, we're in diastole. During that phase is when we're going to see the minimum pressure in the aorta, right? So we're going to see a minimum pressure because we're not adding more blood, but we're not going to go to 0 because we stored pressure in the walls of the aorta. So we're going to continue to have a blood pressure that's going to be able to continue to send that pressure gradient and therefore blood flow throughout our systemic circuit. Okay. Now, these are the two numbers that we're looking for when we take a blood pressure, right? We're really trying to figure out, okay, so what is the blood pressure during systole? So larger number. and what is the blood pressure during diastole, right? So we're trying to figure out how high is the pressure going, and then what's our lowest drop. So we don't do this by like cutting people open and trying to like touch their aorta in order to measure their blood pressure, right? We have ways of going about it that we can kind of approximate this, right? So when we measure blood pressure, we do this with a blood pressure cuff and a sphygmomanometer. So the sphygmomanometer is the thing that's measuring the pressure, okay? The pressure cuff, the purpose of that is to kind of exert pressure on our blood vessels, and we're going to use what we know about the pressure we're exerting on a blood vessel to figure out what the pressure of the blood inside it actually is. So the basic process for this is that if you squeeze down on your arm enough, right, with that blood pressure cuff, right, you put enough pressure on the arm, eventually you're going to squeeze that artery in your arm shut, right? It's not the aorta, but it's close enough, right? We're measuring our blood pressure close-ish to the heart. Okay. So we're compressing this artery down, totally cutting it off with the blood pressure cuff, which is why sometimes if they jack it up too high, like it can hurt a little bit, but like the actual point is to cut off blood flow in the arteries in your arm when you start out taking a blood pressure. Okay. The reason for that is that in order to determine that upper number, the systolic blood pressure, right, we're going to be slowly easing off the pressure on our arm, right? So that blood pressure cuff is going to be deflating, right? And you can feel it loosening a bit. And we're doing it slowly until we hit the point at which the systolic blood pressure, so that maximum pressure coming from the aorta in the arm, is higher than the pressure in the blood pressure cuff, right? So we're still squeezing the arm, but our maximum pressure in the arteries is enough to blow that artery open a little bit at that maximum pressure before it squeezes back down, okay? We can hear that because, as we mentioned when we were talking about the heart, whenever you have turbulent flow, whenever you have flow that's like, partially getting blocked, sometimes getting blocked, sometimes not, right? You can think of it like waves crashing, right? When there are changes happening, we get this turbulent flow that is actually audible, okay? So this is what produces our first sound when we're listening for blood pressure. It's called the carot cuff sound, okay? So that first sound you hear is telling you the maximum number for the pressure in your arteries. So that's our systolic blood pressure that we're going to record first. Now we're going to keep easing off the pressure in our blood pressure cuff because we are also trying to figure out when we hit our lowest pressure, what's our minimum pressure in that artery. So what we're looking for there is like, when do we hit the point where the pressure in that artery is always more than the pressure in the cuff? So our blood flow is just like totally smooth. That artery isn't getting squeezed at all. We're always keeping that artery open. Okay. So that's when we hear no sound. So our sounds disappear because we now have laminar flow, no compression in the artery. So when our sound goes away, that's when we record our diastolic blood pressure. Okay. So we could walk through an image of what's going on in terms of our pressures, right? And then what's going on physically when we're measuring things with our blood pressure cuff. Okay. So we'll walk through it step by step. Okay. Right. So when we start out, we have squeezed down that blood pressure cuff enough that we squeezed down the artery. So we compressed it so there's no blood flow through our artery here, right? So we could record our pressure in our cuff up here, right? So we're seeing that we're easing off the pressure because we're going to try to figure out where do we intersect with the actual blood pressure, but we're not there yet when we start out. This green line is the pressure in the artery. So you can see that the pressure has peaks and dips, right? Because when the heart is pumping out blood, right, we peak up to our systolic pressure. And we head down. And in diastole, the end of diastole, that's our lowest pressure here. Okay, so we're easing off the pressure in the cuff until we hit the point where sometimes that systolic pressure is enough to open that compressed artery up a little bit, right? So we see the first time when we have an intersection between these lines is here. So that's when you would hear the first sound. And then you'd end up hearing another sound here, right? As that artery opens, then you'd hear more sound here, etc. Okay. So we can see that little bit of opening, creating some turbulent flow here through the artery that we can hear. Okay, so we keep going. And we stop hearing sounds at the point where our pressure, whether high or low, systolic or diastolic, is definitely above the pressure in the cuff, right? So now we're not going to hear any sounds at all because that blood vessel is fully open. We got this smooth laminar flow, nothing to crash against, no wave sounds, so we should hear silence. So when we take a blood pressure like that, we give the higher number on top, right? We list our systolic pressure first. That's the first one we hear. So like 110, for example, or 120, right? And then our diastolic pressure is on the bottom, the lower one. So in this example, we got 110 over 70. I feel like usually we're comparing to a 120 over 80 number, right? That's how we see a blood pressure when we measure it ourselves. We can also do some calculations with those two pressures. So if we wanted to measure our pulse pressure, right? So think about how sometimes on some people you can see like an artery bouncing even in the wrist a little bit, or you can feel that pulse pressure when you take a pulse, you can feel the bounce in the artery. What you're feeling is the difference between the systolic pressure and that lower diastolic pressure, right? So you just subtract them if you wanted to find that difference. So our pulse pressure would be 110 minus 70 for a pulse pressure of 40. Okay. But mostly what we're going to be talking about here in this class is our mean arterial pressure. Okay. So we saw before that we're going to be using this number when we calculate our pressure gradient in that flow equation, right? So this is going to be important for understanding the physiology of the cardiovascular system. And what this basically is a weighted average. So we want to remember that we like to not overwork our heart, right? We don't want the heart contracting all the time. So systole is shorter than diastole. The heart should be at rest more than it is fully contracted, right? So diastole is about twice as long as systole is. So when we calculate our mean arterial pressure, instead of just adding together the systolic pressure and the diastolic pressure and dividing by 2 to get our average, right? We have to weight this average because we know that these two phases don't take up the same amount of time, right? So if we were trying to figure out the average pressure in your aorta over a full minute, we'd have to account for the fact that you're going to be in diastole for a lot more of that minute than you are in systole. So all this is that we are going to weight this average. So there should actually be, I think, more parentheses around here. I think the equation might be written a little bit wrong, but we're basically going to add together the systolic pressure, then twice the diastolic pressure, and then divide by 3. So yeah, there should be there and there as well. And we can practice that later. Okay. So we're going to link this back with one sort of remembering that figure from the beginning and some of the features that we expect to see in arteries, and link that up with some features we expect not to see in arteries before we listen to some blood pressures and try and like do this in a practical way. Okay. So we're going to see that our mean arterial pressure is going to be pretty high. We know that our veins in general are low pressure. Our central venous pressure coming right back to the heart is low enough that often we're going to just kind of like wave it when we look at our equations. It's only going to be about 2 to 8 millimeters of mercury for its pressure. Some of our features of arteries are related to that high pressure. Okay, let's take a look. Okay. This is fine. This is a question from your book. I'm not totally in love with this question either. But let's walk through it anyway for a second. Okay. So what we're looking at here, the point, is our arteries are dealing with this high pressure, right? So they have features of the walls that help them hold that pressure easily, right? So the fibrous tissue is the collagen. So that's letting them like remain structurally sound in response to this high pressure, right? And this elasticity of the walls and that low compliance is helping them hold that high pressure in essentially a reservoir that they can then use later. In order to have this low compliance elasticity and high amounts of fibrous tissue, they just need thicker walls in general, and they're going to end up with thicker, smooth muscle in those thicker walls as well. The thing that we're not going to see in any of the arteries out in our body is a valve. We're really only going to see valves in veins. So I want you to think about those semilunar valves as really part of the heart rather than part of the arterial system. And throughout the body, when we see a valve, it's only going to be in a vein. But we'll come back to that when we get to veins. Okay. So let's actually do some blood pressures first. Okay. So what you're looking at here is the sphygmomanometer labeled here. So the like old school way of taking a blood pressure is with a blood pressure cuff, your sphygmomanometer measuring the pressures, and then you'd be using a stethoscope, right, to hear these sounds in the artery. So that's the setup we're looking at here rather than like a digital one that just tells you the number. Okay. So we're going to start with this first example, walk through it together. So what we're looking at now is you're like physically pumping up the blood pressure cup. There's like a little squeezy thing pumping air into that blood pressure cup. So it's setting up. Now we're on purpose letting the pressure down. So we're going to try that again. So watch the pressure go up. The goal of that pressure going up, you're pumping it up above what you expect the blood pressure to be. Then you're easing off the pressure. You're letting a little air out of the blood pressure cuff. We're listening for the first like distinct sound. Now that you've heard it once, I think you can hear how like the sounds of the background versus the actual sounds of the blood sound a little bit different. So we're looking for when does that clear sound first appear, and then when does it disappear? I also want you to notice that we've got this like bouncing a little bit that you can see when we're in that portion of this blood pressure test where we hear sounds? So the official answer for this first one is 98/68. So let's watch that now that we know the answer. Okay. I checked the person who posted it. And then we'll practice one ourselves. I think they might have gotten that diastolic pressure a little off. I think it might be maybe like a 66 or a little lower, but something around there. I'm not going to be quizzing you on the exact numbers in this class, although I suspect someone might in the future. But that's someone else's job. But let's play with a second example for ourselves anyway, because they're fun and they link up to what we're doing. So this one I will ask for votes on. So now we're setting ourselves up. We're blowing up that blood pressure cuff, cutting off our blood flow, easing off. Right. Let's see how we did. All right. So for that one, which of these do we think might match our blood pressure? I made the answer choices relatively far apart so that slight variation in reading that sphygmomanometer is all right. All right, let's see. Yeah, great. So it should be about 94/62. We can listen to it one more time. Some of the sounds you can hear someone like wiggling, probably. You can see that jump starting along with the sound. Somewhere in the 90s for sure. And we're definitely gone by this. Okay. So that's the like practical piece of our kind of theoretical idea of these systolic and diastolic pressures. Okay. So after we go through our big arteries with their pressure reservoir, thick walls, their large diameters, we're going to split and split and split till our arteries get so small you can't see them. Now we're in the microcirculation. And eventually we're going to make our way into the arterioles. Okay, so like our little arteries, next level down. So our arterioles are going to see a big change in pressure across the arteriole, right? So we're going to have flow from the arteriole to the capillaries. But the main thing we're going to think about when we think about arterioles is resistance. Okay. So for our arterioles, this is where we're going to see variation of the diameter, like in real time. All right, like any individual arteriole is going to be sometimes narrower and sometimes wider. Okay. So they're going to be the major player when we ultimately calculate like our total peripheral resistance. That's mainly going to be coming from the arterioles. We're going to connect those arteries to the capillaries, sometimes meta-arterioles, which are kind of like highway bypass systems. We'll take a look. And they contain rings of smooth muscle in their walls. And this is why they can change the radius of their aperture, right? Like they can change how wide they are because that smooth muscle, when it contracts, That's vasoconstriction, narrows down that radius, right? Increases our resistance. And vasodilation, and that muscle relaxes. This arteriole gets wider, flow goes through it easier. We have lower resistance. Okay. So here we see a graph of what's happening with our pressure as we go through our circulation, right? So we see our arteries have a high pressure. Now we've added in making this kind of squiggly because we know we have lower diastolic pressures and higher systolic pressures. So there's some variation depending on where we are in our cardiac cycle, how much pressure we'd see in any given artery. And then we can see that drop across the arterioles, continuing to drop through the capillaries, venules, and then very low pressure in the veins. Yeah. But the arterioles are where we're going to see most of our resistance to blood flow. This is where the majority of our total peripheral resistance is coming for. Definitely more than half, more than 60%. Exactly what percent? Couldn't say. We got this large pressure drop across the vasculature, and we're going to be regulating our resistance here. Okay. So here we can see some different options for our arterioles, right? So at rest, here we see the diameter of an arteriole. And we can see that diameter and therefore the radius can both get smaller and larger, right? So when we're at rest in an arteriole, we're kind of in the middle. So that's our arteriolar tone, okay? So how big the radius of an arteriole is going to depend on how contracted that muscle is. Smooth muscle has this property of tone where you've got this kind of like intermediate amount of contraction at rest. So this arteriolar tone doesn't require like any neurotransmitters and stuff coming in. We don't require hormones to set our arteriolar tone. It's just a property of the smooth muscle itself. Okay. But we can constrict down, decreasing the radius, vasoconstriction, and we can blow those arterioles wide, increase their radius, vasodilate. Okay. Now, reasons we might want to do this. Kind of two of them, right? So one thing that we can do by changing the radius of our arterioles is to change where our blood goes, right? So if we're thinking about changing blood flow to individual capillary beds or individual organs, we're not thinking about changing the overall flow through the system. We're thinking like, okay, spend 70% of it here and only 30% there instead of 50-50 between these two systems. So we would do that by changing the arterioles in a specific part of your body, right? We can also regulate our overall mean arterial pressure, right? So that weighted average blood pressure by varying our arterial radius. And that's when we would be thinking more about changing things system-wide. So changing all the arterioles at once in order to have an effect on our mean arterial pressure. We can do that because remember, right? So our flow is equivalent to our pressure difference divided by our resistance, right? And we know that we have things that we can sub in for all of those. So we know our flow is actually our cardiac output. Our difference in pressure is our mean arterial pressure minus our CVP, except now we know that that's only about 2. So we usually kind of wave our hands, don't actually do the math, but we could actually do the math. And we know that our resistance is the total peripheral resistance. All right. So what we're saying with that second bullet point is that if we change our total peripheral resistance without changing cardiac output, then that would have an effect on our mean arterial pressure. Okay. So fundamentally, when we're thinking about controlling blood flow, blood resistance, one of the things that we're trying to do is distribute blood to all of our organs, but we want to distribute blood to the organs that need it most first, right? When you're digesting food, your GI tract is going to need blood flow so that you can absorb all those nutrients. When you're on a run, your leg muscles are going to need that blood flow, right? If you're at the gym lifting weights, it's arm day, your arm muscles are going to need that blood flow, right? During your day, different parts of your body are going to need blood flow more than others. Okay. So we can do this by regulating the blood flow to those specific organs, to the capillary beds in those organs. And if we were trying to calculate how much blood flow is going to any individual organ, right, we'd still be using that flow difference in pressure divided by resistance equation. But now we're just changing a little bit what we sub in for these variables. So we can assume that our blood pressure in this situation, unless I tell you otherwise, is going to stay the same. So we'll leave our difference in pressure as being essentially our mean arterial pressure. But now that we want to know how much blood is going to an organ, right? We're just specifying organ flow. So now instead of total resistance, our total peripheral resistance, we just sub in how much resistance is in that organ. Right, so this is all the same basic equation. It's just we've specified variables appropriate to what we're trying to figure out. Okay, so here we see this kind of in picture form. So what we're looking at as we start setting things up is what it looks like if we have pretty much going equal to all three of these organs, A through C, right? So we can see we're going from the heart, coming back to the heart. We're going to each of these organs in parallel, right? We're not going in series A, then B, then C. Each of them has the same arterial pressure on one end. Each of them has the same venous pressure on the other end because organ A isn't affecting organ B, their blood flow is separate. Okay. Right. Now, if we think about varying this, that's what we're going to do next, right? Okay. So we're starting out with a difference in pressure. So the difference in pressure, that delta P, is just our arterial pressure minus our venous pressure, right? So that pressure difference is going to be the same for all three of these, A, B, and C, okay? Because we remember that that absolute value doesn't matter, just the difference. Okay. But we can see that flow between these three tubes in this diagram does differ a little, right? So we can see why this might be the case, right? So you can see that hopefully, right, A is a little bit of a bigger tube, right? So a little wider, right? So that has our highest flow. C is definitely our smallest. Hopefully that's visually apparent, right? So that has our least flow, right? Because this is lower resistance for A, higher resistance for C, okay? And B is intermediate between those two. Okay. So we have a total flow here of 3 liters per minute through these 3 tubes. Okay. So we're imagining that total flow of 3 liters is our cardiac output, right? So if we did percentage-wise, how much of that 3 liters is the 1.5 liters going through tube A? That's 50%. How much of 3 is 1? That's 33%, 17% through C. So that's how we start things out. And now we change stuff, right? So what we're doing here is we're showing how could we change flow to organ system B, or how could we sort of change flow to A and C by changing the resistance in some of our arterioles and not others, right? So to specific capillary beds. So in this case, what we've set up is we left A and B the same, but we've squeezed B down a bit, right? So we've narrowed the diameter and the radius of this vessel B, right? So we now have a smaller radius and we have higher resistance, okay? So we can see the immediate effect on B, right? So the flow to B has dropped down, okay? Flow to C has remained the same. Flow to A has remained the same, okay? So this is one effect that we see here, right? We can also notice that in this case, right, we did change the total movement of liquid here. We changed our total flow, right, because we lowered it by 0.5 liters by increasing that resistance in B. So our total system has more resistance, so our total system has slightly lower flow. And we can see that this changes actually all of our percentages, right? So our percentage of blood flow going to B drops down, right? But our percentages still have to add up to 100% of our cardiac output, right? Because that's just how much flow we have. So now A is getting a little more percentage-wise of that blood flow. C is also getting a little more percentage-wise than it was before. So we'll stop here for now. And next time we'll talk a bit more about local factors. Do take a look at like this O2, CO2 hyperemia stuff. We'll talk through it, but it'll be easier to check that you understand it if you've at least kind of worked through the figure on your own a little bit first.